Equations of motion for rigid body in general plane motion. So the rigid body has both rotation and translation. Today's objective: analyze the planar kinetics of a rigid body undergoing general plane motion. This wheel, let's consider that this wheel rolls on the surface without slipping. Okay, so when it rolls, it does not slip, it simply rolls. And slipping means, consider this as a skidding. It does not skid while it rolls. Okay, and this arrow indicates the motion followed by the mass center of the wheel, which is at the center. So mass center has both velocity and acceleration always along this line. So when it rolls without slipping, this is what happens. So it goes from here to the middle point and to the end. Okay. Now at any given instant, let's say at this time, there is a point on the wheel which is in contact with the ground. Do you know what is the velocity of that point? Think about it. So the velocity of that point, I hope you have guessed it right, is always zero at the given instant. So any point of the wheel that is in contact with the ground has zero velocity, and that's why that point is called instantaneous center of zero velocity. Okay. However, when velocity is zero, that does not mean that acceleration is zero. So this point which is in contact with the ground does not have zero acceleration, but it has some value of acceleration. Now, what factors affect the horizontal velocity of the center of mass of the wheel? On which parameters does it depend? So the horizontal velocity of the wheel depends on the angular velocity of the rotation plus the radius of the wheel. And this makes sense because if you consider this as a wheel of the bike, then the speed of the bike depends on the diameter of the wheel and the angular rotation of the wheel. Okay, so if this is center of mass, let's say capital G, then its velocity is omega r, where omega is the angular velocity of the wheel and r is the radius of the wheel. Similarly, the angular acceleration of the wheel is alpha r, where alpha is the angular velocity of the wheel and again r is the radius. But this is true only when wheel rolls without slipping. One more question here. What is the friction between these two? Well, there is always a friction between the wheels and the ground. But what is the value of that friction? Is it static friction, which is mu s times n, that is normal force? Is it kinetic friction, which is mu k times n, or is it something else? Well, we can't say precisely what is the value of that friction because friction is not always static or kinetic. It depends on the situation. So if wheel rolls without slipping, then the friction at any given instant at this surface, at this point of contact between the wheel and the ground, is less than static friction, which is the maximum friction between the wheel and the surface. And then we need to calculate that friction because it's not always static friction, it's less than that. And then the second thing is when wheel rolls without slipping, or rolls with slipping, that means it slips while it rolls or it skids, then the friction is equal to kinetic friction between the wheel and the surface. Okay, so just keep this in mind. We will come back to this point later in the lecture. Okay, so now this is revision from chapter 16. So that's why I have this slide from modified slide from chapter 16, rolling motion without slip. So when wheel rolls without slipping, G is the mass center of the wheel, R is the radius of the wheel, point A is instantaneous center of zero velocity or the point which is in contact with the ground. Alpha is angular velocity, omega, alpha is angular acceleration, omega is angular velocity. And we consider the xy coordinate system here where x is horizontal, y is vertical. So at any given point, the velocity of the center of mass Vg depends on omega and r. So Vg is r omega, and the acceleration of the center of mass depends on alpha and r. Okay, so let's see those equations. So we have already discussed this point that A is instantaneous center of zero velocity, but acceleration of A is not zero. A has some acceleration, and this acceleration is neither vertical or nor horizontal. So this acceleration is a vector at some angle, so it has both horizontal component, which is x, and vertical component, this is y. So this is the equation. Velocity of the center of mass is omega r, and acceleration is alpha r for g. But acceleration of point A is omega square r. And this is again from chapter 16. You can look at chapter 16 slide if you are interested to know how to derive this equation, but or otherwise you can just take it for granted for now. So this is the acceleration of point A. Now what is the velocity of point A? It's 0. So if you just add that equation here, velocity of point A is 0 because that is in contact with the ground. Okay, so we are just building the base here. I'm just revising chapter 16 before we talk about topic 17.5. Remember that G moves along a straight line path and AG is always horizontal. So we start with this reading quiz. So if a disk rolls on a rough surface without slipping, the acceleration of the center of gravity will be blank and the friction force will be blank. And the correct answer is the velocity of the center of mass is alpha r, that is option C, and the friction is less than static friction. It's mu s n. When we use mu s, which is coefficient of static friction, and mu k is coefficient of kinetic friction, this is when things are moving like rubbing each and there is motion, and this is static friction is maximum friction possible to break the motion. Second question, if rigid body experiences general plane motion, the sum of the moments of the external forces acting on the body about point P, which is any point not center of mass, is equal to blank, and the correct answer is Ig alpha plus Rgp cross MAP, where Ig alpha is the moment of Ig is the moment of inertia with respect to center of mass, alpha is the angular acceleration, and Rgp is the vector which goes from point of rotation P to or point of interest P to center of mass G, and this is the cross product with mass multiplied by AP, which is MA is nothing but force, right? You are familiar with this, F equal to MA. So MA is force, so this is nothing but R cross F, which is moment, and this is also moment, Ig alpha. Okay. So let's look at few applications of rigid body undergoing general plane motion. So in this soil compactor, there is a big roller which is used for compacting. Now the roller is not directly driven by the engine. Engine drives the rear wheels. So when engine drives the rear wheel, they push the roller and then it does what it should. Now as the soil compactor accelerates forward, the front roller experiences general plane motion. Do you agree with this? This is similar to the bicycle wheel. So it not only rotates with respect to its center, but at the same time it also moves in the linear direction. So it rotates and translates, so it's in general plane motion. How would you find the loads experienced by the roller shaft or its bearing? So this roller is mounted on a shaft, and this shaft is subjected to some forces as shown in the free body diagram like Gx and Gy. How do we calculate those forces? The forces shown on the roller shaft free body diagram cause the acceleration shown on the kinetic diagram. Is point A the instantaneous center? And yeah, it is. So for this roller, this is the free body diagram. Let me just explain you in more detail what are the different forces. So first of all, this is heavy, so it has some weight which acts through its center of mass, so that is W. Now it's in contact with the ground, so ground exerts some normal force. Then it goes on left, so friction acts on right, so this is the friction from the ground. And then these two forces, Gx and Gy, are the forces exerted on the shaft of the roller because of the weight of the roller and the normal force and the acceleration. Okay. As a result of all these forces, the roller has certain angular velocity and angular acceleration, and roller is heavy, so it has mass moment of inertia Ig. The diameter of the radius of the roller is, let's say, d. Then as a result, the center of the roller has horizontal acceleration, which is AG. Now, in order to solve that problem, in the previous example, in the previous slide, sorry, in order to solve the forces exerted on the shaft, we need to apply the equations of motion for rigid body in general plane motion. So that's what engineers do. So they apply those equations, they calculate these two forces, and you know how important it is to calculate these forces, because you do not want the shaft or bearing to fail while the roller does the compacting operation. Second one, the lone mover is pushed forward with force of 200 newtons with handle at 45 degrees. How can we determine its translation acceleration and angular acceleration? Again, why do we need to do that? Because we just want to make sure that the lone mover is strong enough to sustain all the forces because of the linear acceleration and angular acceleration. We do not want it to fail under the effect of these forces. So does the total acceleration depend on the coefficient of static friction and kinetic friction? And the answer is yes, it depends on both. This is very good example of rigid body analysis in general plane motion. So let me go back to this slide. Yes. So a driver is the person drives the car at some constant speed while the brakes are not applied. The position of the driver is this faded position that's shown in the picture here. Now, during an impact, the center of gravity G of this car crash dummy will decelerate with the vehicle, but also experiences another acceleration due to its rotation about point A. So this is the dummy. So this dummy driver, when the car hits another object, it experiences two different types of decelerations. One is because of the impact, because of the deceleration of the car, and the second one is because of the rotation, this forward rotation of the driver due to impact, because the center of mass of the driver is somewhere here in the body. This is the angular acceleration or angular motion or rotational motion, and the second one is linear motion. So driver goes under both translation and rotation motion. So this is general plane motion. And what is the application here? So how can engineers use this information to determine the forces exerted by the seat belt on the passenger during a crash? So it's very important to apply equations of motion in this example and calculate the total acceleration experienced by the center of mass of the driver, because you know that this acceleration, when it's multiplied with the mass of the driver, results in the force, that is F equal to ma, and that is the force which body of the driver exerts on the seat belt. So seat belt must be strong enough to withstand that force, because if the belt is not strong enough in that circumstance, then it will break because of this high force, and then the result is it will not protect the driver from hitting his head onto the steering wheel. Okay, this can be fatal. So that's why, how would this acceleration impact the design of the seat belt itself? So I have already answered this question. Okay, so these are the three different applications. There are many more, but the main idea here is when rigid bodies in general plane motion, we are interested to know reaction forces, linear acceleration, and angular acceleration of the rigid body. Okay, so equations of motion for rigid body in general plane motion. So this is the free body diagram of rigid body that undergoes general plane motion. So it rotates and translates. These are various forces which are applied to the body, weight of the body which acts through its center of mass, and the externally applied couple moments. Now, as a result of this, rigid body undergoes in general plane motion, and this is the kinetic diagram of the rigid body, where resultant acceleration is in this direction, which is mass multiplied by acceleration of center of mass. Now, this can be projected into x and y to calculate the components of acceleration or the component of the force. By the way, acceleration is ag, but when you multiply that with the mass, you get the force. So this is the direction of resultant force, and this is the horizontal component of the force, this is the vertical component of the force. As a result, rigid body has some angular acceleration alpha with moment of inertia ig. So equations of motion, we use xy coordinate system for rigid body, xy inertial reference frame. So sum of forces in x direction is mass time x acceleration, sum of forces in y direction is mass time y acceleration, and sum of moments about center of mass is Ig alpha. Sometimes it may be convenient to write the moment equation about point P rather than G. Now where is point P? So let's see. So point P is here, and oftentimes we need to write the equations of motion about any arbitrary point, not the center of mass. Then the equation of motions can be written as sum of forces in x, sum of forces in y, and the third one is sum of moments about P. Remember, this is different from previous slide where it was sum of moments about G. Now it's sum of moments about P, which is equal to kinetic moments about P. Now how do we calculate? So for the left hand side of the equation, you need to calculate sum of all these moments of all these forces about point P. So basically you just calculate the force multiplied by the perpendicular distance of each force with respect to point P, and then if it is clockwise you consider that as negative, if it is counterclockwise then you consider that as positive. Okay, so that is for the left hand side of the equation. For right hand side, however, you need to account Ig alpha, that is one term, plus you also need to consider the moment because of the components of these forces, that is x component of the force and y component of the force. Now if you, instead of doing scalar equation, if you go for vector solution, then it's Ig alpha plus moment of this resultant force mag about point P. We have studied this in statics as well, and previously in dynamics as well, to calculate the moment of a force about a point with vector notation, and this can be obtained using cross product. So cross product of this distance or this vector, position vector RGP cross MAG, gives us the moment of this force about point P. So this moment plus Ig alpha is the resultant moment, kinetic moment, and that is the right hand side of the equation, and that's here. Okay, so that equation Ig alpha plus RGP cross MAP. Now MA is nothing but force, and R cross F is nothing but moment, and Ig alpha is also moment. So you can see everything in this equation is moment on left side and right side. Okay. In fact, this was second question in today's quiz at the beginning of the lecture. And now we come back to our previous problem of wheel rolls without slipping. So how do we solve such problem? So consider this wheel on which force P is applied, G is the center of mass, and R is the radius. And this is the resultant free body diagram of the wheel. So for this wheel, different forces that exert on the wheel are applied force P, weight mg which acts down at G, normal force from the ground is N, and the friction force which acts in the opposite direction of the rotation of the wheel. Now when wheel rolls, it has angular acceleration alpha, and when it translates, it has linear acceleration ag. So ag is the total acceleration of the wheel, alpha is the angular acceleration of the wheel. Now in this problem, what we know is we just know the applied force P, and we know mass of the wheel. Now we do not know the normal force, we do not know friction, neither we know alpha and ag. So the equations of motion for this problem is sum of forces in x direction, again we follow the xy system, is magx, sum of forces in y is magy, sum of moments about g is ig alpha. So we have three equations of motion, but can you identify how many unknowns do we have from these three equations? We know P, right? We don't know F, so this is one unknown. We don't know AG, that is second unknown. We don't know N, that is third unknown. And we do not know friction, that is fourth unknown. Yeah, friction is also here. So yeah, that's, we have already counted it. So the fourth unknown is alpha, that is angular acceleration. So the question is, can you identify unknowns? Yes, we have identified them, and our unknowns are this: friction, normal, angular acceleration, and linear acceleration. But we have only three equations. How can we solve for 4 unknowns with 3 equations. We need the fourth equation of motion. Okay, and that's what we are going to derive next. But one thing to remember here is friction is not always mu s multiplied by n or mu k multiplied by n. That depends on the situation. So let's consider there are two possibilities here. Number one is wheel rolls without slipping. So if that is the case, then our equations of motion are these 4 equations, where our fourth equation is one which relates linear acceleration with angular acceleration. So AG is alpha r. Okay, and these 3 equations are from the previous slide. So when friction, so in this situation, when wheel rolls without slipping, then friction is less than static friction. Okay, so friction, this value of F, if you calculate from this equation, and if you compare that value with the normal force multiplied by static friction coefficient, then F should be less than this number. Then you can say with confidence that yes, wheel rolls without slipping. So when we solve this type of problem, what we will do is we apply these 4 equations and we calculate friction, and then we use this equation and calculate friction, and we make sure that this F is less than mu s by n. That means wheel does not skid while it rotates. Okay, so this is case number 1. Second case is when wheel rolls and slips. If that is the case, then this equation is no longer true, because if wheel slips, then linear acceleration is not the product of angular acceleration and alpha. That means we can't use this equation as our fourth equation. So then how do we get our fourth equation? At that time we make use of kinetic friction. Okay. So when wheel rolls and slips, then the friction is equal to kinetic friction, which is the least friction out of static and kinetic friction. So our 4 equations of motions are 3 from the previous slide, and fourth one is friction F is equal to kinetic friction coefficient multiplied by normal force, and at that time AG is not is equal to alpha r. Okay. So using when you solve this type of problem where wheel rolls without slipping, this is the example of that compactor machine or the lawn mower. Then apply either this equation if you precisely know that wheel rolls without slipping, or you apply the second set of equation if you know that wheel rolls and slip. Okay, so that's for the friction rolling problems. So the general procedure for analysis of rigid body undergoing general plane motion is given on this slide. So the steps are: you first establish the XY inertial coordinate system, draw the free body diagram and kinetic diagram, then specify the direction and sense of acceleration for center of mass AG and angular acceleration of alpha. If necessary, compute the mass moment of inertia IG. And then if the moment equation sigma mp is equal to kinetic moment is used, use the kinetic diagram to help visualize the moments developed by the components of the resultant force and mass moment of inertia. And then apply the 3 equations of motion and solve for unknowns. Okay, and particularly when you come across the problem where wheel rolls without slipping, then check for slip or no slip. First make that assumption and check your validity at the end. Okay, so be consistent in your assumed direction for the problem, and remember that the friction force always acts in the direction opposite to the motion.